think I'm going to go ahead and start my introductory remarks while anyone else still files in. So yeah, big welcome to all of you. My name is Jonathan Rubin, and I am the chair of the Department of Mathematics here at Pitt. And this is a Science Revealed event. So Science Revealed is a series that I founded with Satish Iyengar from Statistics, in which we sort of take off our disciplinary hats and put on our scientist hats. And the goal here is to try to share with as wide an audience as we can results that highlight the capacity of science and the ability of science to develop objective information about a variety of things, as well as the way that science works, including its limitations. And so today's event is very much in the spirit of that. We'll see things about scientific findings as well as limitations. The other goal of the event is to highlight some of the amazing work that happens here at the University of Pittsburgh, which I think is strongly represented today. So to tell you more about that and about today's event, I'm going to turn things over to Cassie Quigley, who's the moderator for today. And I just want to say thank you to all of the panelists and to Cassie very much for eagerly signing on for this event. So thank you.
Yeah, thank you so much. Yeah, thanks, John. It's a pleasure to be here. My name is Dr. Cassie Quigley. I'm an associate professor of science education, and I'm also the chair of the Department of Teaching, Learning, and Leading at the School of Education. It's my pleasure to moderate today's event. I'll just talk about a little bit of organization for today and provide you with a bit of background and then turn it over to our panelists. So we have four dynamic panelists today. Each of them will speak and share screens with some slides for you. And then after each panelist, we'll have time for about one question while we're kind of transitioning to the next panelist. But at the end, we hope to have plenty of time for a really robust conversation across the four panelists. Our panelists really vary, as John was saying, in terms of discipline, perspectives, and their research, both methods and findings. So we're really pleased to have everyone here today. Also, you'll see at the bottom that you have the option to pop a question into the chat under the Q&A. Please do so at any time. I'll be fielding those questions. If you want to direct it to who the panelist is that the question goes for, please, just include their name so we can remember as we file along through the afternoon. And at this time, I would also just like to send a special thank you to Ellie Caden and Clara Weebler, who helped to get the word out about this event. And thank you all for joining. So at this time, I'd like to introduce our first panelist. We have selected an order of the panelists that for us made sense as we sort of were moving through the conversation. And we're going to begin with Dr. Dane Ban. Dr. Ban is an associate professor from the Dietrich School of the Department of Geology and Environmental Science. Dan combines hydrology, geomorphology, biogeochemistry, ecology, and spatial analysis to examine fundamental human interactions with landscape components, and particularly with fluvial or stream urban systems over the last centuries. So at this point, I will turn it over to Dan.
Thank you very much. And thanks to everyone who's joined us today. It's nice to see such a good turnout. And so I'm going to be starting off. And I chose a picture, for in Southern California, maybe you might see Florida throw up some palm trees. But this is kind of the iconic thing that you want to think about when you're thinking about Pittsburgh. It's just, there's no limit to the number of just terrible things spewing out in black and white photos. Black and white is good. It means it happened a while ago, but it's a different thing. So I work oftentimes in soils in urban systems. And I guess the one question you always get asked is, can I garden? Am I in danger? And so what the rest of the speakers today are going to talk about things that are, how we make the rules about what's safe, what's not safe, things like that. So, we have a pretty good idea that if you're near a house, historically used lead to make paint white. So rain is going to wash that lead off. So if you're near an old house, a house that was built before 1986, thereabouts, you want to be really careful about the soil here. We know that because of the gasoline additive that was used wholesale across the continent in the gasoline, near road areas, you want to be safe. But in these areas that are in between, we don't quite know exactly what's going to be happening, how safe they are. And you want some rules of thumb. You should always test and make sure. But one of the questions that has come of this, sort of in my mind, is what is the role in these what we've been calling background soils in Pittsburgh from this intense industrial history? And so this work really grows from a master's student of mine, Alex Maxim. She's now at Georgia Tech in a PhD program, but she, most everything you're going to see today is her work. She should be talking, but she's dissertating. And so the question is these are all of the industrial sites from the Rivers of Steel archives. The archivist down there just made a list of every single thing that had any sort of association with the steelmaking industry and put it on a map. We put it there. And so the question is what happens with all of these emissions? Where did they end up? Are there places that are worse than others? Other things like that. We expect it probably to be moving towards Pittsburgh because most of our winds are coming from this direction, but we don't know where. And we were lucky enough to have a collaborator at the Allegheny County Conservation District who had a class spend some time going around to areas that were not near historic buildings or modern buildings, not near roads, and in areas that had trees in it or were obviously not disturbed in the last short period of time. So this is the more or less grid. So it was based on a grid, random selection of spots within the grid. These are the locations where we had a soil sample. Alex, I showed you in the last picture. This is John Burgess, our collaborator. He's now at the university he's the new director of the Pittsburgh Water Collaboratory. But Alex took all these soils, did a whole bunch of different chemistry. And since I only have 10 minutes, we're not going to get into that. We're going to be talking mostly about results, but trying to understand the patterns in these background samples across the city of Pittsburgh. And so we use a number of different techniques to try to come up with ideas of how things match up. So here we have it shown two ways. This is lead on the left and cadmium on the right. You can see vaguely in the background the three rivers. So here's Bruno Island, here's the point. And the circles are in proportional size to the concentration of lead in the soil. So you can see locations that are more concentrated than another. There is one really anomalous cadmium concentration on Bruno Island. We don't use that in the rest of the analysis because it's such a big outlier. But what we used is a technique called kriging. And what that does is it takes all these locations, it takes all the difference between the location, the nearest locations, and then the next nearest location, comes up with rules about what a location in between might look like. And so one of the things that we started to notice is, we had highest concentrations over in this eastern half of the city, which is good because we expected the wind to be blowing things this way. But the other thing is we started to get this elongation up in north. And this other thick white line here is what we call the paleo channels. And I'm going to show that to you next. And The paleo channels are a result of these rivers back during these times of huge glacial melt. These rivers were much bigger. You know, that view from Mount Washington formed in a matter of years. It was a tremendous amount of flow. It cut down very, very quickly in the relative terms. But if you look at the city, you can still see old courses of the river. So right here are the modern rivers. You can see them here. This is the hill shade of the topography. But right in here, you can see these paleo rivers. These are the places that we are most intensely urbanized in Pittsburgh. This is the Homestead, the Shady Side, the Morningside, Highland Park. And that's because these are flat. And these are the paleo river valleys. But as you recall, when we started looking at where those emissions ended up in the soil, there was this elongation up from areas down here. And so what we wanted to do, what we could also do then was try to understand where some of these things might be coming from. So what we did is we plotted, you know, all the chemistries in these different samples, the concentration of lead versus the concentration of manganese, of zinc, concentration of cadmium versus the concentration of zinc. And what we could do then is we could look at something like the shale. The shale is what the rock that's going to be underlying the vast majority of Pittsburgh, more or less. And so if these chemistries started moving in one direction off of the shale, so for example, the lead, there's a lot more lead in the shale for a given amount of zinc than there is. What could be driving that? So we have a line here for bulk coal. That's the chemistry of bulk coal, but this is a secondary lead smelter. And that's a story we're not going to be able to get to today in this formal presentation. But there's the other case is we could also see it in another direction. So again, here's the shale. And in some cases, we're enriched in zinc. And in some cases, we're enriched in cadmium. And zinc, you know, it seems to be in the coal fly ash, maybe is a little bit higher. But the cadmium, you got the secondary smelters, maybe that's not such a clear signal, but this coke signal down here is a far outlier. So this is the chemistry of a coke emission. And that makes sense because the coking temperature is about where cadmium should be boiling off. And so what we did then is we took a look at the ratio so we could map this relationship. And so if you take a look at where zinc is 400, cadmium is about 1. So this is a ratio of 400 to 1 and you zinc to cadmium. So something like that would be right about here on this scale. So in this area, or above the shale, we're relatively zinc rich. So the areas that would be down here in the coke are going to be down here like this. We've also plotted on this map things like the Shenango Coke Works, which is a historical coke works, the LTD Coke Works, which was something that was closed down, you know, many years, it's decades ago now, it's still there. But you can see in these areas which are just downwind of the Shenango, and then communicating through these paleo channels with historical facilities like the LTD Coke Works, that's the spots where we have the most depressed, or the most cadmium in these soils. So we're interpreting this as, you know, these valleys, these low spots, particularly during atmospheric inversions, tended to hold more emissions, allowed it to deposit more, and this is consistent with some of the air stories we might be talking about now. And you know, I would love to be able to say that this is all just historical and these were failures of policies past, but you know, this is still going on. This is a picture of the Clairton Coke Works. This still impacts, if you're living in Pittsburgh, your life every day. And we don't know. We don't know how to solve this problem. It's been something that I've been here for 15 years, and it's something that needs to be addressed. And hopefully, we'll talk a little bit. The rest of the folks will talk a little bit more and tell us why and how. You know, I need to acknowledge some funding from National Science Foundation, Heinz Endowments, and some DSA as funding sources, but just, these historical emissions are haunting us. They're arranged in sometimes surprising patterns. And, as we look to the future, we need to think about preventing the same mistakes we've made in the past. With that, I'm happy to pass it off to the next panelist.
Thank you, Dan. If there are any questions that anybody would like to drop in the Q&A for Dr. Bain, we can do that now. And I can also provide those at the end when we have more time for Q&A. We will be, next up, we'll have Dr. Aaron Barchowski. But while Dr. Barchowski is getting his slides ready, Dan, I just wonder, you're starting to begin to think about the ways in which policy and science aren't working together. But I just wonder if you could share just a few of your thoughts on how you think policy could be better informed by the science that you all are discovering.
Oh, how it could be better informed. Well, but the policies aren't driven by the science. So maybe it's the scientists thinking more like more vitally and less like we're removed from this whole process and more engaged. I do think that thinking about this in a way that is, responsive to community members and community problems really goes a long way to addressing these things much more effectively than if we sort of come from it, the classic, I'm from the government, I'm here to help. I'm from the academy and I'm here to help. No, we should go and say, how can we help? What are the questions you need help with?
Yeah, thanks, Dan. Yeah, that's I think really important, right? As scientists and as politicians, right, to learn to be able to speak similar language, right, to one another. And I know Dr. Barchowski, Aaron is going to be speaking a little bit about that of the public health side. But Dr. Barchowski is a professor in the Department of Environmental and Occupational Health in the School of Public Health. Aaron is a metals toxicologist who, for the past 30 years, has investigated the mechanisms of disease caused by exposure to metals and environmental contaminants. He is best known for his discoveries of how arsenic in drinking water promotes cardiovascular and metabolic diseases, as well as how inhaled metals promote pulmonary disease. All right, I'll turn it over to you.
Okay, thank you very much. And yes, maybe I will illuminate some of your question to Dan. And it's always great to follow Dan. I think this might be our second or third symposium where he tells you all the things that are moving around because of industry, because of hydraulic fracturing or energy extraction. But the questions that we ask are, so what and how much? Pretty much, is there a hazard to health from an exposure to these metals? And then, of course, what level of exposure is going to put you at risk of disease? And so that's where a lot of our research goes, but also we'll end up with an alternative question to the policy questions. So metals are rather unique. Most people have an aversion to looking at the periodic chart, but I bring it up just because it brings up 2 points. Metals are elemental. They are elements. Man doesn't create them. All we do is just move them around, spew them all over the place, and cause differences in exposure. And is there significant amounts of exposure to metals? Well, the Agency for Toxic Substances and Disease Registry ranks priority cleanup sites for the amounts of various compounds are there. So if you look at some of the worst contaminated sites, you find that the top 10 contaminants, 40% of them are metals. The top 3 are metals that all of us are familiar with. And number 7 is cadmium that Dan's talking about. So these are actually contaminated Superfund type sites or whatever, but it also speaks to the prevalence of the metals in the environment. I will point out real quickly to number 4. Number 4 is a big problem over in Ohio today and the last couple of days because that train that derailed had a number of tanks of vinyl chloride. So again, we do horrible things to the environment and to our populations with various exposures. So the other important thing about the periodic chart and metals is that a large majority of elements are metals, and a lot of life evolved on this planet to either use those metals as essential elements in enzyme reactions, basic metabolism, coping with our environment, but also if they can't use them and they're toxic, to come up with mechanisms to avoid the toxicity, or at least to evolve alongside of something like an arsenic that is the 21st most abundant element in the Earth's crust. So we have just evolved from bacteria all the way up to humans to be able to manage arsenic toxicities. But what we need to do is to understand the science behind how these metals interact with each other, how a toxic metal might substitute for an essential metal to now create a toxicity. What are the mechanisms that are causing ill health, but then also how much is responsible for doing that, a dose response, if you will. And I'll bring this up again with the concepts of non-essential metals and essential metals. Non-essential metals are essentially metals that we never really, or no biology really utilizes, and consequently they're toxic to the species. And I'll give you 3 or 4 examples there: arsenic, lead, cadmium, chromium, and something like a lead will rob the body of calcium mechanisms and cause toxicity in a number of tissues. Cadmium really accumulates in the kidneys and causes a lot of renal damage and some other diseases. Arsenic is what I've made my career on, especially with the cardiovascular disease. And that graph is a dose response relationship for risk of coronary heart disease from arsenic exposure in drinking water. It's a significant meta-analysis because there are over 250,000 individuals contained in those graphs. So exposures from high to low, and showing that that line at 1, which is the no risk line, that the arsenic becomes toxic with a threshold of somewhere around 5 parts per billion, or a little bit less than 5 parts per billion. What does that mean? That means that our current EPA drinking water limit of 10 micrograms per liter is actually above or twice as much as that threshold. So that drinking water limit that was set to protect against cancers may not be protective against a cardiovascular disease. And I'm involved with the current assessment of risk by the EPA, looking at now non-cancer disease endpoints, including cardiovascular disease, including cognitive development in children, and others, that where we're going with the research is trying to find the disease that is most sensitive to the arsenic and question whether that's where we actually should be setting regulatory limits for protection. So you see that line, the dose response line for the arsenic for a non-essential is essentially a linear type relationship. Where we get into real tough questions of regulatory policy is when we analyze the dose response curves for an essential metal. Picking manganese as an example, we know that we need adequate levels of manganese to have good neurological function. We supplement baby formula with manganese to make sure that we have a level that's going to give us good health. But this study that was done in children across the Ohio River, I think over in the Shippingport area, which is somewhat rural, but is actually heavily industrial. They looked at neurocognition outcomes in the children. And what they found was this is actually a low socioeconomic community that was very concerned about their exposures. And what you see with that inverted shape of a curve is that below a certain level, the children had cognitive problems, decreased full-scale IQ, decreased perceptual reasoning. But then when you went above a level, you also wound up with, again, lower IQ and lower reasoning. So this actually makes a very tough conundrum for regulatory policy, because how do you set a limit for a compound that's actually important for your health? And certainly we need to be careful when we're doing that. Why is this important? Well, that manganese in the children that at the higher level, that was near a plant that was producing a lot of manganese or a lot of manganese waste. With hydraulic fracturing, we're moving it around in environment and into people's well water. So there's a good bit of concern there. I'll speak to Dan's question about lead and where we can have success. And this is actually, EPA throws this up and says this is one of the most successful interventions that was ever done. This is the Clean Air Act. And what you're seeing there is the percentage of children who have lead levels above the recommended level of 10 micrograms per deciliter. And you see back in 1976, 1980, when the Clean Air Act was coming into vogue, when they were removing that lead out of the gasoline, that 88% of kids were over the recommended blood level. And by the time you get to 2004, it's down to 1.4%. Fantastic success story and a good reason why you set regulatory limits. But it's also controversial whether that's an adequate limit to protect. Some people say that no lead level is safe for children. That's up for debate and for the regulatory agencies. But what's important is that we keep on causing problems. We have Flint, Michigan, where we changed the water chemistry in the public water supply, mobilizing lead out of pipes and into children. So the graph that I show you show that we've got generations of kids who are spared all the lead exposure, and maybe they're going to be developing better. But now we go back and we've created a whole new generation where we have to take care of their public health impacts for the poisoning. And I say, true public health impacts because I grew up around Baltimore, Maryland, and they had a huge lead problem, and they had a large population of children in the inner city who were exposed to lead to the extent that they had behavioral problems and neurological problems caused by that lead exposure. One gentleman who is actually in part of a lawsuit as a child, and his family got compensation, was Freddie Gray. And if you remember who Freddie Gray was, he was a Black man who died at the hand of a police because of his behavioral problems. So yes, it is a generational impact. So I'll finish with another question that just doesn't get to trying to do science to find out how much is going to cause a problem, how much we should regulate down to. And with something like arsenic that's so prevalent in the environment, or how do we clean up everything everywhere, I actually work on questions of what if we can't regulate down to a safe exposure? What if it's just economically not feasible to get rid of the exposures? Or an exposure, what is an exposure that protects against all diseases? You know, so what if we can't regulate down to that level? And so we do mechanistic research to identify effective ways to reduce disease susceptibility and burden. Can we change nutrition? Can we change something proactively in populations that might be exposed to a hazard like a lead and reduce their disease burden? And I will say that Dan made a great recommendation that if you have an urban garden, test your soil, and that's a great program that could be done probably through extension agencies and spare a lot of people toxicities. The other basic reason why we do our mechanistic research is if we can identify how the metals are causing the problem, we might find an effective way to reverse the disease in the exposed. What if we can find a way to reverse the neurological cognitive problems caused by a lead exposure to a child? We currently are doing some work with arsenic where we're looking at the communication between healthy muscle and healthy cognition. And we find that in arsenic exposed mice that have changes in connectivity in their brains, that if we rehabilitate their muscle, we can actually rewire their brains. So we're working on processes like that to, again, come up with, if we can identify a way to figure out who's exposed, can we fix it? And I'll leave it there.
Wonderful. Thank you, Aaron. I really appreciated, that your talk and sort of the continuation from Dan's from the science and why we have certain metals located here to kind of analyzing a little bit about, some of the concerns we should have and how measures are not always telling us exactly what we need. So really interesting. Thank you. In the interest of time, we're going to move along to our next presenter, Tina. Tina Nadeau is an associate professor in the Department of Environmental and Occupational Health at Pitt School of Public Health. She's a dedicated educator and focuses on equity and environmental leader. She is passionate about environmental justice and has worked toward efforts that allow people to enjoy the natural environment free of pollution. She has over 20 years of engineering and air quality experience and has mentored early career environmental professionals and has managed student interns in environmental fields. All right, Tina, I'll turn it over to you.
Thank you, Cassie. So hopefully I'll be able to continue a theme moving along that's really us focused on science and policy and understanding how, once we know the science that's leading to environmental degradation, how do we start to have appropriate strategies for mitigation? And some of those things are, focused on the science, the basic science research, but I want to really look today at the local participation in federal environmental standard setting. And I'm going to show the oil and gas methane rules as a case study. Part of what I get to do one of the hats that I wear here in environmental occupational health is serving as the director for community engagement for the Center for Human, Environmental, and Equity Research. And a big part of that job will be engaging communities in research. There are similar mechanisms that go with engaging in research as in going with engaging in regulatory development. But a space that we don't know a lot about is the efficacy of a lot of the engagement practices that take place. So I'm going to take you all through the oil and gas methane rules and some of the regulatory challenges with that particular effort, and then take a very hyper-local look at feedback from Pittsburgh and Allegheny County and see how the EPA has addressed that feedback. So just very quickly, I won't go through this much since we have such a short amount of time, but just to show the policy process. These 5 components are generally taught as here are the things that one needs to think about when developing policies. You start with defining your problem. That's often done for federal agencies outside of the agency themselves. There's agenda setting. You'll see that come into play in the discussion a little bit later with transitions from one administration to another and how that shifts the agenda. That also makes public engagement particularly tricky. Policy development shows up. In this case, we're going to look at the actual regulations of the policy that's being developed. And we won't talk much about implementation or evaluation, but just know those are components that come in there as well. Another piece that folks need to keep in mind is that often there are competing policy interests that govern actions. So often when we start thinking about environmental regulations, and I'm going to say we in terms of broader public community and environmental advocacy groups, the focus is more around the part of the definition that the Office of Environmental Justice gives, which is that no group of people should have a disproportionate burden of environmental harms, and that we want to include risks that come from negative environmental consequences of, in this case, industries. However, when you're inside of the agency and developing regulatory standards, and as I think as Casey noted, I've had the opportunity to develop multiple national air quality standards. The primary policy driver tends to be Clean Air Act language that gives firm guidance and limits on the authority that an agency has to actually try and tackle environmental hazards. So for instance, the oil and gas standards that we're going to look at are developed under Section 111 of the Clean Air Act, which are the new source performance standards. And the language from the Clean Air Act directs the agency to look at the best system of emission reduction. So this is a technology-based focus here, and to consider cost in achieving reductions and any non-air quality, health, and environmental impacts and energy requirements. There's also an iterative review process that we'll talk about in just a little bit, but just know there that there's a bit of tension that you can see there between the more lofty policy goal that the Office of Environmental Justice puts out and the very prescriptive language in the Clean Air Act for how to actually look at some of the emission categories that we're dealing with. So hopefully I'm going to ask the question, but hopefully it's very evident. Why are we talking about oil and gas as a specific example? And the answer is twofold. One, the wells are ubiquitous across the state. You can see there in that top map that's showing there, and both of these were pulled from the Pennsylvania oil and gas mapping tool. But you can see there in the top map that there are oil and gas wells across a good swath of the state. The blue that you see there is showing conventional wells, and the red that you see unconventional wells or fracking sites. Pennsylvania has over 100,000 active well sites. There are hundreds of thousands of inactive well sites, at least 300,000 or so in the Southwest Pennsylvania area. And the majority of those inactive well sites are unplugged. And we care about unplugged wells, particularly because those well sites tend to leak different pollutants, which I'll talk about in just a moment. And until they are properly plugged and capped and remediated, they serve as a major environmental and health hazard for folks in the surrounding areas. The lower map, just to show, is a map of the abandoned wells just in Allegheny County. And so when you think about the timeline of impact of the oil and gas industry in this area, you have to think about what's happening with the abandoned well sites that are not properly plugged, what's happening with conventional well sites, and what's happening with some of the newer fracking sites. So oil and gas wells emit a wide range of pollutants. The rulemaking is called the oil and gas methane rule because methane is one of the key pollutants that's targeted. Methane is a very potent greenhouse gas. It has high warming potential. And in addition to methane, there's also CO2 emissions from oil and gas wells. We know as well that volatile organic compounds are emitted from these sites. VOCs can be a precursor for ozone formation. And within that mixture of VOCs, there are many air toxics. There's other pollutants that are emitted as well from sites that you see there listed. So when we think about the health impacts from these pollutants, first, when we segregate out the climate health impacts, there's a whole range of human health concerns. There's increased respiratory and cardiovascular disease, increased injuries, premature deaths that are associated with extreme weather events. Those extreme weather events and longer-term changes in climate lead to changes in the distribution of food, increase in waterborne illnesses, and other diseases. If you're looking at some of the non-climate health impacts, there's increased respiratory distress and emergency room visits due to that elevated ozone with that secondary formation. And again, a lot of the VOCs are air toxics, which means that many of them have potential to be carcinogens. So I debated on, do I make this as convoluted as possible or as non-convoluted as possible? But I want to show the history of how the oil and gas industry has been regulated just from the air standpoint for news sources. So again, this is the new source performance standard. It is an iterative rulemaking process. And that means that once the standards are promulgated, there is a statutory timeline associated with it for how often you have to review those standards. So the NSPS for oil and gas were initially promulgated in 1985. There's an 8-year review cycle that's attached to that, meaning once it's finalized, within 8 years, the agency should look at those standards and see, are they still achieving what we want them to achieve? Have there been advances in technology that would allow you to cost effectively move the needle so that there are even more stringent requirements in place to help reduce those emissions? There are open proposed revisions to the standard right now. I think many folks on this call are aware of that. In 2021, the EPA issued a proposal that put significant new restrictions in place for oil and gas wells. And then in 2022, the agency came out with a supplemental proposal. The supplemental proposal was almost like saying, here's proposal part 2. That's not a commonly used method. Generally, you would have an action proposed and then you would move forward with the final. But here, knowing how complex the technologies were for the oil and gas industry and truly how complex of a problem it is nationwide, there was a 2-step process for getting public feedback. So the supplemental proposal is still open for public comment currently, should be closing fairly soon. The agency conducted high levels of outreach for this action, and I won't go into what that looks like just based on time, but just know what they consider to be the highest level of engagement is some of what you see here in this rulemaking. I do want to point out that there was a 2018 proposal, and that rule was finalized in 2020, and then it was immediately rescinded in 2021. And hopefully, if you're thinking about this in terms of presidential administrations, you're recognizing that 2020 was the end of one administration, the end of the Trump administration. 2021 was the start of the Biden administration. And so that's why you see the pullback of the regulations. Think about it from the perspective of someone trying to engage. You commented on a rule, that rule went final, it gets pulled back, there's a new rule proposed, a supplemental to that proposal. So for someone who commented in 2021 on the first action, hopefully in 2023, that rule will be finalized so they can see if their feedback was taken or not. So I'm really interested in looking at some of the qualitative work that happens here when it comes to engagement and getting public comments on regulatory actions. If we look at oil and gas as an example, and if we try and take a hyper-local look at Pittsburgh, and Pittsburgh's a great place to look when you're talking about air quality regulations, because this is a city that is full of environmental advocacy groups. There's a lot of resources that go into getting groups prepared to understand what's in the regulation, to comment effectively. There are also a lot of resources spent on the regulator side with trying to reach key populations and get their feedback. So who responded to the rule? The 2018 version of the rule, or the 2018 proposal, received 500,000 comments. Out of those, 2,100 were unique comments. What that means is that the vast majority of those comments were mass mailer campaigns. So a large environmental organization might reach out to 200,000 people and have them submit feedback or submit a form letter and sign their name. That's counted as an individual response, but a non-unique comment. And it's important because EPA has to respond to every comment that's received. But when you look at those 2,100 unique comments, over 90% came from individual private citizens. The remaining 10% were split between industry, the mass mailing campaigns, environmental advocacy groups, state, local, and tribal agencies, and academia. Pittsburghers wanted to see, and at this point I'm shifting I'm having to move so quickly, but just to know, I'm shifting to the 2021 proposal. The 2018 proposal, for quick backstory, because it was under the Trump administration, it was very much a relaxing of rulemakings. And so a lot of the local feedback was simply a statement of opposition to the rule. So there wasn't anything specific asked. There was a statement of opposition. Those statements were not taken into account. The rule was finalized as proposed. But if we look at what did Pittsburghers and Allegheny County residents want to see in the oil and gas standards, there were some unique requests from Pittsburghers. Pittsburghers wanted to see life cycle emissions testing for the wells. This has some overlap with some of the provisions around monitoring for some of the smaller wells and getting some new provisions put in place. So that overlaps with what we see with some of the larger campaigns. There was a request for unused wells in an area to be plugged before any new wells are created. So one commenter suggested a radius, I believe, of 10 miles before you would have to plug all of the unplugged wells before you could do any new well drilling. There was a request or a comment suggestion that we look at setback requirements for homes and schools, and then that bankruptcy loopholes be addressed. The other comments from Pittsburghers were echoed by either national campaigns or by smaller campaigns. And I'll just note here too, given time, again, when we look at Pittsburgher comments, the majority came from individual letter writing and not from the mass mailer campaign. So is the feedback from these local organizations or from these local individuals, how is it being taken into account? If we move from the 2021 proposal to the 2022 supplemental, we can get a really good window into how the agency is planning to operate. We don't know what the final standards will be yet because they haven't been finalized. That should happen later this year. But the fact that there's a supplemental proposal, it sheds a lot of light into where the agency is likely to go and to what they heard in the 2021 comments that they are actively moving forward with. What I can share just from early review of some of the qualitative data, there's not a lot that's pulled from local Pittsburgher feedback that actually made its way into the final or into this, the supplemental proposal. By contrast, if you look at what some of the larger mass mail campaigns requested and Pittsburgher feedback that went through those, you see a lot more inclusion of key components and key requests such as leak detection and repair and pulling in smaller wells for monitoring. You see that actually echoed and responded to in the supplemental proposal and will likely be part of the final regulation. So I'll just say, as we think about human environmental interactions and how all of these advocacy groups that we have in Pittsburgh, across the nation, and all of the efforts that we're spending on engagement, there really is a lot of space for more work on understanding the efficacy of different levels of engagement and how that engagement actually influences environmental standard setting. Are we seeing ultimately reductions in environmental harms based on the efficacy or based on the advocacy from some of these different units of feedback, individual versus small organization versus national mass mailing campaign? What strategies are really working to help pool community feedback as a collective? That's, something that I think that a lot of folks are interested in terms of best using resources, but it's something too that really needs to be explored from a research perspective so that there is a more consistent body of work around community engagement. And then just really understanding, again, the type of comment and level of comment that actually influences policy amendments. So I will stop there and turn it over to Cassie.
Wonderful. Thank you, Tina. That was really fascinating. And just while we're transitioning, we do have a couple of questions in the chat, but a super quick one based on what you're saying. And I know this is early work with the qualitative findings. It seems like, though, that the mass mailers that we all sort of participate in, I'm sure as, engaged citizens here on this call, it seems that those are an effective way of connecting into regulations versus the unique individual. Is that what you're sort of seeing?
Well, I think that's complex, because if you look at the 2018 iteration, there was a lot of mass mailer energy around opposing the standards. There wasn't a specific request as to how to amend the standards, but just opposition, and that was not considered. So I think there's a lot of questions around what's the interaction between the feedback, what can actually be evaluated from a scientific perspective. General support or opposition is not so easy to evaluate. And so there are some spaces where large scale interactions is not very effective.
Yeah, super interesting. Thank you so much. All right, last but certainly not least, we have Dr. Shanti Gambar Rabindaran, who is a professor of Pitt's Grad School of Public and International Affairs and the Dietrich School Department of Economics. Her book, which we see right here, America's Energy Gamble: People, Economy, and the Planet, details how political and financial and legal institutions entrench fossil fuel dependency, but how efforts shift to renewable energy are gaining traction. Additionally, her edited volume, The Shale Dilemma, A Global Perspective on Fracking and Shale Development, details the decisions of countries to pursue or eschew shale development and the impacts of shale extraction on local communities. In 2021 through 2022, she served on the National Academy of Sciences, Engineering, and Medicine Study Panel on enhancing the U.S. chemical economy through investments in fundamental research in chemical sciences. She has also served as the August Wilhelm Scheer Visiting Professor at the Technical University of Munich, Germany. All right, Shanti, I'll turn it over to you.
Okay, great. So I'm going to talk about the science policy interface, and it's great that I'm following Tina and Do's presentation, because I will be focusing on the Clean Air Act, but specifically the National Air Quality Ambient Standards. So, okay, why is this not moving? Okay, so reminder to everybody, science is not partisan. Both Democrats, Republicans, and independents have supported science to inform public policy. So a quote from President George H.W. Bush, who is U.S. president from 1989 to 1993, now more than ever on issues ranging from climate change to AIDS research, government relies on the impartial perspective of science for guidance. President Bush was very key to addressing acid rain under the Clean Air Act amendments 1990. Another quote from Sherwood Bollett, who is the chair of the House Science Committee between 2001 and 2006. He was a Republican from New York, and he served on the Bipartisan Alliance for Climate Protection. he said that no member of any party should look the other way when basic operating parameters of scientific inquiry are exploited for the sake of political expediency. Wholesale, ideologically based or special interest driven rejection of science is bad policy. So just want to make the point, science is nonpartisan. Okay, so now I'm going to look at the national air quality standards, ambient air quality standards, and in particular, I'm going to look at the particulate matter. And I will look at this issue during the Trump administration. So in general, we kind of think that there should be scientific evidence and consensus that a pollutant harms public policy. And from that, public policy would respond to protect public health. In reality, we have this interference where you have special interests manufacturing doubt on the science and special interests capturing regulatory process. And then we see that public policy fails to respond to protecting public health. This is not just my argument. This is also an argument that Naomi Oreskes and Eric Conway made in Merchant of Doubt in 2010, and David Michaels made in his book, Doubt is Your Product in 2008. So particulate matter pollution, where does it come from? Among others, from fossil fuel combustion. So particulate pollution from burning fossil fuel is responsible for 1 in 5 of premature deaths worldwide. And this comes from a study by Voha et al. So the National Ambient Air Quality Standards is written into the Clean Air Act, and the standard should be set to protect public health with an adequate margin of safety. So what does adequate margin of safety means? If there is uncertainty, you want to bend towards being precautionary. Okay, so there's a scientific process. This is a flow chart showing you the scientific process for setting the National Ambient Air Quality Standards, and this was used till 2018. So we have first with a workshop on science policy issues, and importantly, we have an integrated review plan, and then we have an integrated science assessment. So basically looking at the studies that are relevant for setting the standards of PM. And then we have the Clean Air Scientific Advisory Committee, or CASAC, which will review the science. And because CASAC only have 7 experts, we do have a PM scientific panel made out of 20 independent scientists with specific expertise on the pollutant. And these 20 scientists provide expertise to complement the expertise on the CASAC, the one that's in yellow in the picture. So based on so CASAC will evaluate the science, and then the agency will finally go through decision-making process, and the EPA administrator will take into account what CASAC says and makes the final decision. Okay, so this is the flow chart. And now I want to point out what happened in the last determination of the NAAQS standards. So we had 2 types of interference. One, an interference in the process, where you see a removal of independent scientists from the process. And you also see a change in the analysis, where a contrarian approach has been adopted. So in the past, the scientific staff in the EPA would actually advise the EPA administrator on who to select for CASAC based very much on their scientific credentials. In the last round, we see the EPA administrator selecting several CASAC members, including the head of CASAC, who took contrarian positions. What do I mean by contrarian positions? Contrarian position does not mean, avant-garde science information that is paradigm shifting. Instead, what contrarian position means is that there's a cherry picking of the data to come to a certain conclusion. And we also see that the EPA administrator dismissed the PM panel of scientists, which had the expertise in PM. But the scientists were very, very cool. They were amazing. So they continued their work as the independent PM panel of scientists, and they produced their work for the public to see. And in terms of analysis, the CASAC had emphasized a contrarian approach. What specifically? In its view of causality and its response to uncertainties. And I'm going to explain this in detail in the next slide. Okay, so this picture tells you a summary of what happened between the 2009 assessment and the 2019 assessment. So within a decade, we have more information on the effect of PM10, on the effect of PM in general, on health effects. So this picture is basically telling us that between 2009 and 2019, we have more information that now has told us that there is a link between a likely causal link between long-term exposure to PM 2.5 and the likelihood of cancer. So that's like one example you can pick up from this table. So in other words, the integrated scientific assessment is telling us that now there's more information showing that there is now causal relationship between PM and additional categories of health outcomes that we didn't really understand in the previous ISA. So the independent PM panel, this is a group of independent scientists, recommended a tightening of the PM standards. So the annual standard was recommended to be tightened to 8 to 10 microgram per meter cube from 12 in the previous standard. However, KSEC recommended to leave the PM standards unchanged, and they cast doubt on the evidence of causality and amplified scientific uncertainty. So basically, 5 members of the KSEC, 2 dissents on the KSEC, recommended to leave PM10 unchanged. In 2020, the EPA administrator decided to leave PM standards unchanged. In 2021, the EPA announced a reconsideration of the PM standards. Okay, so another reminder, particulate matter is bad for human health. 4.2 million people die prematurely due to long-term exposure to PM2. Okay, what happened during the process? So pre-2007, the professional staff of EPA provides recommendation on the selection of subject matter experts. So basically recommending the 20% PM panel and the 7-person KSEC. These are academics with subject matter expertise, including epidemiologists. For the KSEC during the Trump administration, the EPA administrator picked KSEC members with contrarian positions. The EPA administrator dismissed several academic members from KSEC. The 7-person KSEC no longer had an epidemiologist. The administrator also dismissed the 20-person PM panel and hired consultants. And the argument was that EPA academics who receive EPA grants are now all excluded from advisory panels. So this means we're excluding academics with subject matter expertise. Next. So just to remind you what the consensus view had been prior to 2019. So this is in the previous assessment of PM and also 2 dissents in the KSEC. What did they say? They said that the evidence now supporting a causal relationship between PM 2.5 and mortality is even more robust now than it was in 2009. There is no credible evidence since 2009 to refute this determination. So they were basically arguing against the KSEC majority view that suddenly in 2019, there's no longer adequate evidence on the causal relationship between PM and health effects. And this, the difference is coming from the standards of what is the evidence that counts in the analysis. So in the past, the scientists have taken the weight of evidence approach. Basically, you consider multiple lines of evidence in peer-reviewed studies. You look at consistent epidemiological evidence, you look at experimental models in animals and humans, and basically come to a conclusion based on this multiple level of evidence. And based on that, the scientists argued that there is a causal relationship between PM and health effects. However, in the contrarian viewpoint, it narrowed what counts as evidence. So basically, they said that, only manipulative causality can establish causality. So what does this mean? This means that the only study they are willing to look at is if there's randomized controlled trials. So some subject matters are exposed to high levels of PM and some subject matters are exposed to low level of PM. This does not happen in real life. It's unethical to run this. And interestingly, this is the same argument that tobacco lobbyists had used against the scientific findings on the link between tobacco and health effects. Manipulative causality can also come from changes in public policy that leads to reduction in pollution and then looking at what happens to health effects. In other words, sort of really, really narrowing the kind of an evidence that would count as causality. Okay, so in the previous 11 panels that looked at the National Ambient Air Quality Standards, they basically use the weight of science approach. Okay, the next thing that we see is also this approach to uncertainty. In the past, scientists used this idea based on what's written in the Clean Air Act, that when there is uncertainties, that is a reason for anticipatory protections. However, the KSAC members who take the contrarian position said that scientific uncertainties would justify no additional protection. And they specifically said that these standards that are much lower are adequate if we give weight to scientific uncertainties. So very contrary to what is actually written in the statute. And I want to call your attention to a 1995 climate denial memo. So Frank Lutz explained how to generate uncertainty and reduce public support for climate change. He said you need to continue to make the argument of lack of scientific certainty central to the climate change debate. If the public believes that scientific issues are settled, then the position on climate change will need to change. So this idea of, amplifying uncertainty has been there to deal with climate denial, and now we also see it in PM. Okay, so one final thing I want to bring to light is when we look at the battle against regulation, the previous administration didn't just use specific attacks on individual rules. They actually took a very much blanket rule approach. So what is the rule that can be put in place that basically would strike down all protective rules? And it was called the Strengthening Transparency in Regulatory Science rule. If you don't read this rule properly, you would say, oh, transparency in science, that's a good thing. However, this is a little bit Orwellian in the use of the title, because it turns out that what this proposed regulation would do is that it would exclude valid studies that form the basis of science linking pollution to public health. It would exclude epidemiological studies, and it would actually give the ability to the EPA administrator to do cherry picking. We are very lucky because the courts in 2021 actually vacated the rule. And it was because of a procedural issue that the EPA had improperly claimed good cause to make the final rule effective. So this is very much, we got saved by the skin of our teeth kind of story. I think what is very worrying is that historically we see support of science we see support for science informing public policy, and we see that it was a non-partisan value. Many Republicans, Democrats, and independents continue to value science today. And I think what's important is to realize that this attack on science is not in a rearview mirror, and we actually need to maintain a vigilance that this does not change. And finally, I want to show you something that's really worrying. In the year 2000, this is a survey from the University of Chicago. So if you look at the year 2000, there's no difference between Democrats and Republicans in terms of their support for science and scientific institutions. By the time you come to 2001, you see a divergence here. 64% of Democrats support science and scientific institutions, but only 34% of Republicans do. So this is really worrying because science, which used to be bipartisan in its support, has now become polarized. I will stop there. Thanks.
Wonderful. Thank you so much, Shanti. And thanks to all the presenters. We had a nice kind of pathway through both starting with science with Dan's work on understanding, why we have certain toxins in our environment, to Aaron's talk on understanding some of the mechanisms for, beginning to regulate that, and how it's important to think about many different diseases as we set those levels, to Tina's talk on learning about how we start to use science to create policy, and what that means in terms of advocacy and how we're taking up people's suggestions to finally Shanti's talk, really then thinking about the importance of what the policy says so that as it's enacted, what we're hoping, right, the policy means is what is being enforced. So really quite incredible. I can see in the chat that we had a couple questions already answered. So please feel free to add questions to the chat. While we're waiting for those to populate, John, do you want to unmute and ask your question?
Sorry, I had to wait to get permission to unmute. Thanks, Cassie. Yeah, I thought that a really important point came up. Well, many important points came up in all of the presentations, but one that struck me from Shanti's was this issue of causality. And so I don't know the makeup of our audience, but I just wanted to comment on that and ask a question, which is, so what a really easy way to understand proving causality, right, is that we take two groups of people who are otherwise identical, and we perform some manipulation to one, like we expose them to intense lead levels or something, and we see a very different outcome due to that exposure. But in these epidemiological settings, we can't run experiments like that. We certainly wouldn't want to, even if someone let us. So can you clarify for people who are less familiar with the field and so on, like how do epidemiologists establish causality when they can't do those types of experiments where they actually manipulate something in a group and watch what happens? Could you give us a generally accessible answer to that? I guess Shanti, but certainly anyone else too.
I think Aaron is the expert here, but my 2 cents for the people who are not scientists, you do have to look at consistent evidence across different ways of getting evidence. So the one aspect of it would be the epidemiology study. And then you also have to see consistent evidence in the animal studies and also at the molecular level. So you basically are trying to search for evidence that's consistent across different models and different scales.
I would absolutely echo that. And I think what Shanti put up with, the weight of evidence is very important for determining whether something is a carcinogen or whether something is a cardiovascular toxin or other things. And I think that EPA is improving their tools in trying to evaluate the scientific literature, but one of the biggest problems is that there's not enough science or epidemiology to back up regulating certain toxins. In our case, there's a lot of literature on lead or cadmium or arsenic, but emerging toxins that we should be concerned with, there's just not that same level of evidence. And we often go to what Shanti was talking about with uncertainty and questionable use of uncertainty in the policies because we're saying, oh, we only have rodent exposures, et cetera, the National Toxicology Program did. And the problem with that is that scientifically, it's difficult to really interpret non-human studies. And as John, you said, it's really pretty unethical to do the human studies. Unfortunately, it's all retroactive human exposure studies. So it's a really difficult conundrum, I think, for policy.
But I just want to emphasize that for several pollutants, there is enough evidence where it's consistent across different models. I think that it's important to remember this uncertainty applies to a subset of chemicals, but the science is good enough to take action for many pollutants. And the kind of the use of amplification of uncertainty and the narrowing of causality is really, really dangerous, because think about climate denial, right? If you come with climate denial and you want a narrow view of causality, you need planet A where you're running the experiment and planet B where you're not running the experiment. It doesn't work, right? So we have to be very careful about any kind of narrowing of causality that's actually kind of serving a specific purpose at the end.
Yeah, and I'll also say that for something like arsenic that we've known has been a toxicant for millennia, the use of the risk assessment, et cetera, to delay appropriate changes in the regulations has been amazing to me. I've been involved in advising EPA on revising the risk assessment for arsenic for over 20 years. And we may get to a revised risk assessment maybe in a year or two. There's a new revised scientific advisory board, but then translating that into potentially changing the arsenic standard is another political struggle. So yes, we can do our best to give you all the causality and plausibility for how an arsenic causes disease, but policy is above my pay grade.
Great, thank you so much. We have a couple questions in the chat. Elise has just popped a question in the chat that says, controls are definitely important in an epidemiological context, but without them, policymakers don't like to approve regulatory levels. But without regulatory levels approvals, we can't run these experiments. It's definitely a rough cycle to escape, in my opinion. Yeah, thanks for that, Elise. Yeah, and before we take Julia's question, which I think is a nice kind of final question to think about, I'm just curious because, as we're all sort of thinking about the impacts of this work and what it means, both either, how it ends up in policy or how that policy is enacted, I think a lot about communication and how we're communicating to one another, and particularly as a science educator, right? So what are some of the ways that you think that we could improve the way that we communicate science and or policy?
I'll share that, one thing that I think is important when we think about improving communication is to really approach things with a lot of cultural humility and to interact with the intended audience and seek their feedback on what are their preferred communication strategies. Are we hitting the mark? Are we way off? I'll just share as an anecdote, a group that I led did a lot of work to try and communicate some of the challenging scientific and technical issues around air quality regulations to the general public, and thought that we had done a great job. And feedback that we got after a public training session was, you lost me. We really didn't know what, there was too much jargon, although we thought we had de-jargoned the language. And when we asked for feedback at what point did some of the written communication lose you? The response was the first sentence. So I think there's a lot that needs to happen with interactive and proactive engagement with the intended audience to make sure that we are speaking their language and meeting them where they need to be met in terms of getting the communication to the right channels.
Yeah, wonderful. Thanks for that, Tina.
There's a group called Climate Social Science Network, and they actually, this is like a super great group in terms of working on climate communications. So if you go to their website, they explain terms that come naturally to people working in the field, but the generic public does not understand it the way we do. Like even the word uncertainty. Uncertainty could, to us, means we don't know where the error bars extend to, However, for the general public, uncertainty could mean we don't know the answer. And this can be exploited by climate denialists in creating a wedge in understanding. So it's Climate Social Science Network, if you look them up.
Thanks for that. Dan, were you?
Yeah, I was just going to follow up on both of those. And I think that communications is a conversation. It's not. And then I think that there's a temptation and an availability bias amongst us that if we create the most perfect communication strategy, then, you know, everything is going to fall into place because we can see the logical end game. But I really think that, you know, part of it is also, you know, you have to give up maybe some authority. You have to listen to the question that comes back. And I think that's part of places where things start to fall short.
Yeah, absolutely. Thank you for that, Dan. We have a question from James in the chat. He says, we usually consider regulation chemicals as single entities from single sources. How do we again consider cumulative risks from multiple hazards as important? I think this might be for Aaron or from Dan, for Dan.
Yeah, I mean, this is a question I have too. I mean, when I was an undergrad, the next big thing was going to be mixtures and the toxicology of mixtures, but it's like the sheer number of combinations. And like there's the study of salmon, and they were dying in the Pacific Northwest. People had no idea why. And they did all these different toxicological tests. And then finally, there's some obscure plasticizer that ends up getting used in tires. And it's just deathly to the salmon. And it's not even a mixture, but the needle in the haystack for some of these physiological responses is, whoo boy. And so, you know, just like the gradient, you have to think, you know, the combination of a wee little bit of cadmium and a whole lot of lead to a wee little bit of lead and a lot of cadmium that's a lot of real estate. So, I mean, I'd love to do it, but I don't know how. Maybe Aaron does.
I don't know how, but I have a number of investigators who are trying to figure out how. And I will thank you, Jim, for your question. And Jim's a colleague. His office is actually right next door to mine. But this is a $60 billion question because what we're trying to do, Tina alluded to, creating a Center for Human, Environmental, and Equity Research. We're trying to actually approach this question by analyzing what we call the exposome. And the exposome is it is the totality of your exposures, not just the contaminants in the environment, but also social and other determinants of your health. But I think, Jim, really the more we can go to big data modeling of the exposures, that would be a combination, would really help indicate where we should look. But as an experimental mouse guy who's trying to figure out these toxic mechanisms, I think it's a huge challenge that everybody in toxicology is trying to figure out. How do you really adequately test whether a certain mixture is going to cause a problem? And I think it's really going to come down to a lot of in silico AI type work that will get us to being able to test it in biological systems.
Oh, I just want to give the name
go ahead,
of the person. Sorry, Tina, just very quickly. The person I would recommend us reading is Susan Hassel. Her last name is Hassol. She works a lot on climate communication and has good tips for instructors like us. Go ahead, Tina. Sorry.
Problem. I was just going to speak a bit to the regulatory side of things as well, because I think that was part of Jim's question. And, it's a very complicated regulatory landscape when you start moving towards cumulative burden protective standards. And there are some spaces where there's a lot more consideration of cumulative hazards. Shanti talked about the NACs, and you really do start to see cumulative air impacts. You don't see multimedia impacts necessarily, and I think that gets to a question that was posed earlier. But for a lot of the stationary source regulations, there really is a limit in authority that doesn't allow for some of the cumulative considerations that are aspirational to EPA and the Office of Environmental Justice, but are not supported by statutory authority. So I know there have been several bills proposed in Congress that would expand some of the authorities that would allow for cumulative impacts consideration. So there's a challenge on the science side as well as a challenge on the policy side, and a space where science needs to help guide policy. Policy would also help push science along. And there are some developments that would allow for cumulative burden consideration. So there's a lot that can be done based on the science that we have now, but there's probably more of a policy constraint than anything.
Wonderful. Thank you. Thank you all. So we're at the end of our time here today. I think that was just such a wonderful panel and a robust discussion. And I do just want to take a moment to thank a couple people who are behind the scenes here with us, Jason Irwin and Carol Mullen. Thank you for all your help in setting this up and getting the word out and the technical aspects of today. And then just last but not least, thank you panelists for joining us today and spending your afternoon with us. It was incredibly interesting. John, do you want?
No, I thanks for mentioning that, because we couldn't have done this obviously without the panelists or any of the other people that you mentioned. And having an audience was very nice too. So I hope that people took away some interesting messages from this. And if you did, keep an eye out for future Science Revealed events. I think they've all turned out to be really stimulating and brought out a lot of interesting issues that we might not think about if we're not immersed in fields ourselves. So yeah, thanks very much.
Thank you all for organizing it and inviting us.
Yeah. And I will say, I'll open myself up to, if anybody has any questions, feel free to email.
Bye. Thanks,
Thank you.
everyone.
I thank you.
Well, okay, I was going to say goodbye to everyone, but now it's done. Thanks, Jason.